What is a planet? Like so many seemingly simple questions, this one is anything but. The problem is that the answer lies in antiquity. In a view of the world first assumed, then questioned, then contradicted, and finally, after a revolution, banished. The term planet is rooted in the idea of change first embraced, then qualified, and then mathematized. In short, the idea of the planet is an anachronism. As we discussed in episode 3.5 of this series, a planet was originally anything that moved with respect to the stars in the nighttime sky. The word itself comes from the Greek word for that which wanders. In this definition, one shared by most of the ancient peoples that surrounded the Mediterranean, but most notably the Mesopotamians, there were 7 such objects. From the sun that provided warmth, light, and life, to the slow-moving object eventually named Saturn by the Romans. And just as there are 7 planets, so are there 7 days in a week, 7 seals, 7 trumpets, and 7 bowls of wrath. In those cultures and traditions that take from the heritage bequeathed by the people of the Fertile Crescent, 7 is a number of cosmological significance because there were 7, and only 7, things that moved in regular patterns through the unchanging heavens. The classical Greek philosophers, wanting little to do with gods and the like, built models of the heavens that emphasized the changes in the positions of the planet. The sun, the moon, and the 5 lesser lights could be thought as arising through unchanging change, the unending turning of perfect spheres made of stuff not found on the unmoving earth. In time, these models would be changed to better account for the observed motions, but the spheres were never discarded, and the earth was never thought to be like the rest of the planets. For centuries this model held. Through war and famine and the collapse of great civilizations it survived. Through plague and pestilence, the rise and fall of kings and clans, the 7 planets continued their unending, unchanging course through the celestial realms. So perfect were these motions that they were thought at times to govern affairs on earth or to reflect the will of the gods, or in time, the one true God. But then came Copernicus, and for the first time in human history, the definition of what a planet was changed. The sun was made immobile, and only the moon continued to orbit the earth. Now there were just 6 planets, even though there were still 7 objects that wandered through the heavens. They didn't now all orbit the sun. Soon Tycho would demolish the crystalline sphere, and Kepler would banish the circles. Galileo would reveal new worlds around Jupiter and raise the question as to whether these new stars should be thought of as planets. His ideas would prove troubling enough that he would be censured, and the teaching that planets were anything other than what the ancient Greeks had thought would be officially banned in Catholic Europe, even if that ban was frequently ignored outside of parts of Italy and Spain. In Protestant England and Holland, it would be the Keplerian-inclined experimental philosophers who would set aside questions as to what a planet was and focus instead on understanding how to characterize the motion. This movement would culminate in the great work of Newton, whose system of the world would put forward a picture of the heavens that would banish, once and eventually for all, the notion of a stationary earth at the center of all things. In Book 3 of the Principia, the globe to which humanity was bound by that same gravitational attraction that affected all things in the universe was one of 6 worlds that orbited the sun, along with a smattering of comets, one of which would provide an early celestial proof of his synthesis. A planet was now that which orbited the sun in a regular fashion, Halley's once every 76-year apparition notwithstanding. The moon was now a satellite, as were the Medicean stars orbiting Jupiter. For 50 years, there were 6 such objects, until the sharp eyes and rigorous observing of a German expatriate in England would add 1 to that list to again reach 7. Over the next few decades, Additional objects would be added and then removed, further muddying the answer to our question. In 1846, an eighth object was added by a French genius in a stunningly brilliant application of Newton's laws. Along with that, however, soon some claimed even more worlds, one that would prove ephemeral and another that would be found in 1930 by a Kansas farm boy come astronomer. And so for decades, there were 9 planets inscribed in school books and taught to children across the world. 9 planets, so called by an unexamined definition that seemed to arbitrarily exclude some objects while enshrining others. That is, until the 1990s, when new telescopes and technologies began to reveal that in the distant and vast expanses of the outer edge of the solar system, there lurked other objects that also orbited the sun. Named for a Dutch astronomer, these largest residents of what was known as the Kuiper Belt, by some estimation closer to comets than planets in terms of composition, loomed larger and more massive than Tombaugh's Pluto. And so, in 2006, the International Astronomical Union, the largest organization of professional astronomers in the world, took up the question of what should and should not be called a planet. They attempted to define what had not been well defined in over 400 years. Their answer was exactly what one might expect of a collaborative effort, that of a bureaucratic committee. It was technically well defined in its designation that lacked any romance and was understood only by those fluent in the specialist language of planetary research. In it, Pluto was demoted, and the solar system once again contained only 8 designated planets. The outrage that followed was as predictable as it was unhelpful, based as much on familiarity and nostalgia as in anything scientific. In this episode of the Scientific Odyssey, and the next, we'll see if we can follow the twists and turns, the successes and failures, the hard work and wild speculation of 2 centuries of trying to determine just how many planets our solar system has. Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a many-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery. Series 3, Finding Our Place, Episode 29, Planet Hunting. On one evening of March of 1781, the Herschels of Bath settled into what was becoming their usual routine. Brother William had come to the English countryside to teach music after deserting from the Hanoverian army in 1780. He was the director of the orchestra of the town and gave lessons on the side, but the profession was mostly just a way to pay the bills. His passion was something altogether different. He had come to Britain with his sister Caroline, with whom he shared his love of the stars. The two had become hooked through that gateway drug of astronomy, observing Saturn through a telescope. Caroline had a way with the calculation and construction of mirrors that would give the clearest images, and William had the keen eyesight and steady hand to draw from the instruments images of great clarity. They had been working together, along with their younger brother, since as early as 1774, to make systematic observations of the heavens, and after relocating to Bath, had decided on a new project. This effort was to do an observational analysis of what are known as double stars. The goal of the project was to observe as many pairs of stars that were found in close angular proximity to each other in the sky as they could, to determine if the stars were really physically associated with each other or if they were at different distances from the Earth, but just happened to coincidentally lie along the same line of sight. A way to think of this would be comparing two automobile headlights which are physically related as compared to two distant street lights at distant differences that just happen to line up in your line of sight. On March 13th, as he did most nights after dinner, William set himself down with what was one of the few working Newtonian design telescopes in all of the world. Designed and built in a collaborative effort of the three siblings, the 6.2-inch Newtonian reflector was the largest of its kind anywhere in the world, and was judged to give images as good as much larger refracting telescopes across Europe. Among the targets that evening was a double star found at the boundary of the constellations of Taurus and Gemini. As Herschel gazed upon the first star of the pair with increasing magnification, it remained a point of light. However, when he switched to the other, he found that it was fuzzy. Moreover, as he increased the magnification of the telescope by changing the eyepiece through which he was looking, the object got larger. It was not a typical star. In his observing journal, Herschel recorded, quote, "The lower of the two is a curious, either nebulous star or comet," end quote. Over the next month, Herschel viewed the object over and over and found that it moved ever so slightly against the background stars. As he did so, he became convinced that it was a comet, though, if this were the case, it behaved rather oddly for a comet. It wasn't growing larger as one might expect, nor was it producing any signs of a tail, as would be expected. Finally, perplexed as to its nature and finding no new evidence that would shed light on the problem, Herschel published his results in the Philosophical Transactions of the Royal Society. With this done, others could now turn their instruments to the object and make additional measurements as Herschel returned to his original project. In May, two mathematicians, one Russian and one French, took the accumulating data and calculated the orbit of the object, finding it to be both circular and further from the Sun than Saturn. In this, they discovered that it was not a comet, but rather a planet, the first discovered since before antiquity. Just as the British Empire was about to lose 13 colonies across the Atlantic, the Hanoverian transplant in Bath was proposing to name a newly discovered world after the nation's monarch. Fortunately for posterity, the rest of the astronomical community objected to Herschel's proposed Georgium Sidus, or George's star, and eventually agreed upon the name that would make the now seventh planet the butt of the oldest joke in astronomy. The discovery of Uranus, or Uranos, as is most properly pronounced from the Greek, is now marked to Herschel's initial observation of March 13th, 1781, though it can actually be found in the appropriate positions in the star charts of both Ptolemy and Flamsteed. For his part, Herschel was given a stipend of £200 and a knighthood in order to move his observatory to King George III's Windsor Castle, where he and his sister would continue to do remarkable work. It was Laplace, using the data of Uranus's orbit, who came up with a generalized way of calculating orbits for celestial objects in the opening salvo of what would become a glorious career of celestial mechanics and mathematics. These efforts would produce the work we discussed in our last episode that accounted for the changing orbital speeds of Jupiter and Saturn. It also produced a series of predictions for the orbital motion of this new world, predictions that would become very important as time went on. In all of his work, Laplace was committed to the underlying truth of Newton's world system, even as he worked to construct a more powerful mathematical framework in which to understand it. As Laplace would write, quote, "There is no truth in physics more indisputable and better established by the agreement between observation and calculation than that all celestial bodies gravitate towards each other." End quote. This would become the guiding principle for all analysis of celestial motion for the next 120 years. However, As Laplace was working out this fiendishly complicated mathematical framework, others were noticing a pattern in the orbits of the planets, one that would have intrigued someone like Kepler. If you look at the average orbital distances of the planets expressed in astronomical units, the distances are 0.4 for Mercury, 0.7 for Venus, 1 of course for Earth, 1.52 for Mars, 5.2 for Jupiter, 10.4 for Saturn, and now something in the neighborhood of 20 for Uranus. What a number of people, including Johann Daniel Tydeus and Johann Albert Bode, saw was that it was possible to reproduce the sequence of planet distances using actually what was a fairly simple mathematical series, known as the Tydeus Bode Law, or more often now, just Bode's Law. The sequence goes as A equals the quantity 4 plus x divided by 10, where x is a sequence of numbers that starts at 0 and goes 0, 3, 6, 12, 24, 48, 96, etc. What you can see in the sequence is that, with the exception of that first 0, each number is found by doubling the previous number in the sequence. Thus, the first term in the mathematical expression is 4 plus 0 divided by 10, or 0.4, which is the semi-major axis, or radius of Mercury's orbit. The second term is 4 plus 3 divided by 10, or 0.7, which corresponds to Venus. The third term produces 1 AU, where the Earth's orbit is, and the fourth term corresponds to Mars. There was no planet found in the Newtonian system for the fifth term, while Jupiter and Saturn are found at the distances provided by the sixth and seventh terms, or 4 plus 48 divided by 10 and 4 plus 96 divided by 10, respectively. The first person to discuss this was actually the Scottish mathematician and astronomer David Gregory in 1715 in his book Elements in Astronomy, with Tydeus publishing in 1766 and Bode publishing sometime around 1772. While it is clear from the historical record that Bode believed that the relationship could be used as a guide in the search for additional planets, no one else in the 1770s gave the idea any credence, as it was just assumed that there were no other planets to be found. However, when the discovery of Uranus was announced at the distance from the Sun predicted by the next term in the sequence, 4 plus 192 divided by 10, or 19.66 AUs, a lot of people and a lot of astronomers sat up and took notice. With the recognition that a planet might be too dim to see with the naked eye, the long-held belief that planets would be easy to see was then discarded. This led to the recognition that there was a gap at 2.8 AUs where the Bode relationship predicted there would be a planet between Mars and Jupiter. And as you might imagine, the race was on to find a new world. In 1801, the Italian Catholic priest and astronomer Giuseppe Piazzi, who would, by the way, become a person who would compile what was probably the greatest star chart of his time, containing over 3,800 stars and their coordinates, announced that he had found an object orbiting the Sun at roughly the distance of 2.8 AUs, as predicted by the equation. Working from the Church's observatory in Palermo, Piazzi had been recruited by Franz Xaver von Zach, editor of the Monatliche Correspondenz, in 1800 to join a group of 24 astronomers that would search the sky for objects that would match the Tydeus-Bode parameters. However, before he agreed to be part of the project, he observed an object on January 1st of 1801 that had comet-like characteristics, but that moved slowly and regularly enough through the background stars that he began to entertain the idea that he was looking at something else. Over the next couple of months, he would observe the object some 24 times to more precisely establish its orbit, but then its motion took it into the glare of the Sun. Piazzi would dispatch letters regarding his observations to a number of astronomers, including Bode, to establish his priority of discovery and to allow other observers a chance to make observations. Unfortunately, determining where to look once the dim object emerged from the part of the sky dominated by the light of the Sun was going to be difficult. In this time of need, a young German mathematician by the name of Carl Friedrich Gauss, would derive a mathematical expression that allowed for the efficient calculation of an object's orbit from just a few observations. On December 31st, almost exactly a year after its initial discovery by Piazzi, the new planet was observed to be just exactly where Gauss had said it would be found by Heinrich Olbers, he of the famous astronomical paradox. Piazzi suggested it be named for the Roman goddess of grain, Ceres. And so, there was, it seemed, an eighth planet. However, the excitement was short-lived. Early in the next year, Herschel made additional observations of the planet with a better instrument and found it to be surprisingly small, only about 250 kilometers in radius or so by his estimate. While this turned out to be too small by a factor of 2 or so, the planetary status of Ceres was called into further question when Olbers discovered a second large object orbiting the Sun at roughly the same distance, something he named Pallas. Smaller than Ceres, Pallas confounded astronomers, and Herschel suggested that these be placed in a new category of celestial object he coined asteroids. While there weren't many takers for this idea at first, it began to find new adherents when, in 1807, 2 more objects, called Juno and Vesta, were added to the now growing list of things found at roughly 2.8 astronomical units from the Sun. For a time, these kinds of researches would be suspended due to the Napoleonic Wars and their aftermath. But when, in 1845, a 5th object was found, it was decided that Herschel's intuition had been correct. In 1850, Ceres and her sister worlds were demoted to become part of an ever-increasing group of objects known as the asteroid belt that seemed to stretch from about 2.4 to 3.8 astronomical units, a conglomeration of objects that by the year 2000 contained nearly 100,000 identified members, ranging in size from a few kilometers to 1,000 kilometers in the case of Ceres. Back in 1802, following his discovery of Pallas, Olbers had suggested to Herschel that the objects had once been a part of a larger world that had been destroyed by some cosmic internal explosion or cometary impact. As more and more objects were identified, this hypothesis grew in popularity until the dynamical work by later physicists and planetary scientists began to show that a much more likely explanation was responsible. Something that had to do with the gravitational influence of Jupiter preventing the aggregation of material from smaller bodies into a larger one. We'll return to this idea in a later episode of the series. Nevertheless, with the discovery of objects at the distance from the Sun at 2.88 AUs in the early 1800s, it looked to a lot of people like the Tydeus Bode Law was a good rule of thumb for determining the distances of the planets and predicting where new ones might be. Now, before we move on to other matters, I'd like to take just a moment to evaluate what this Tydeus Bode Law was. What we have is a relatively mathematical expression that seems to match the positions of the planets pretty well. Well enough, in fact, that it guided a research program to find new worlds that was actually successful. What it wasn't, though, was an explanation of any sort. My colleague and friend, Dr. Todd Timberlake, has rightly asked whether it should be called the physical law, and it behooves us to examine that question just for a bit. It's pretty clear from the historical record that a good number of astronomers of the late 18th and early 19th century regarded the law as such, as a physical law. On the other hand, it's pretty clear that they have no underlying theory to explain why the law worked. There's nothing in Laplace's or Lagrange's reformulation of Newtonian mechanics that suggested such a relationship would even exist, or if it did exist, why it existed. And yet, there it was, and it had been successful in making at least one prediction. Thus, for the next 45 or so years, it's pretty clear that, like the emerging gas laws in chemistry that applied to only ideal gases, there was a gap between characterization of a physical pattern and an underlying explanation for the causes of that physical pattern. So, for astronomers in the early 1800s, the Tydeus Bode Law was held to be a physical law even if it wasn't well understood. Of course, with all of the closest in slots, at least closest into the sun, now filled, the next possible place for a planet to exist was going to be at about 38 or so astronomical units, twice the distance of Uranus from the sun, something thought to be out of reach for the telescopes of the time. Besides, there were bigger problems to address. The now 8th or 9th, depending on how you counted, planet Uranus wasn't moving the way it was supposed to, a fact that threatened to undermine Laplace's perfectly Newtonian mechanical universe. Urbain Le Verrier was a very talented and interesting man. Educated at the prestigious École Polytechnique in Paris, his training had been in chemistry, where he studied under Joseph-Louis Gay-Lussac, who is best known for establishing the relationship between the temperature and the pressure of an ideal gas. Upon his graduation, Le Verrier had taken work in a tobacco plant as a chemical engineer, working with phosphorus to produce matches. Work that, for all of its practical applicability in the 19th century, wasted his rather prodigious mathematical talent. He labored there for 7 years until an assistantship in astronomy opened up at the Polytechnique. He felt he had the talent in the industry to do the work, to get up to speed in a field, and so he applied. Impressed by his industry and diverse experience, he was offered the position. Upon his arrival, he found that he had inherited the legacy of Laplace, who had died in 1827, and a problem that was beginning to become something of a crisis in the astronomical community. In 1821, the French astronomer Alexis Bouvard had published a series of observational tables for Jupiter, Saturn, and Uranus based on previously acquired observational data regarding their orbits, and he used Laplace's mechanics to do this. While the predicted positions of the first two worlds were confirmed by subsequent observations, the position of Uranus very quickly began to deviate from its Newtonian orbit. As the discrepancies got worse, it became apparent that celestial mechanics was in a bit of a bind. Now, before we go on, let's pause for just a minute to do a little thinking about how science gets done. In the traditional model of scientific inquiry, what Laplace had developed was an advancement of Newtonian mechanics that took into account all of Newton's laws of motion and forces. This theory was then used to explain the motions of the objects through space, something it did very successfully for Jupiter and Saturn. However, when applied to the motions of the recently discovered Uranus, it failed. The theory had made a prediction, and that prediction had been wrong. So what could be done? One thing would be to say that the observations were in error. Unfortunately, these were almost immediately checked, and they all seemed to be pretty good. In other words, Bouvard's analysis was sound. Another answer would be to say that Newtonian gravity, that very strange action at a distance force, was either different than everyone thought, or was represented mathematically in a way that didn't take into account the fullness of its physical reality. This would be the suggestion of German astronomer Friedrich Wilhelm Bessel, who suggested that the universal gravitational constant found in Newton's work wasn't actually a constant. Its value changed as a function of distance. A third possibility was that gravity was just flat out wrong. The force either didn't exist or wasn't an action at a distance force somehow, and that it should be rethought along the lines of Descartes' long-discarded mechanical philosophy, as Leibniz had attempted to do. Neither of these ideas, the second or third, seemed very likely, because Newtonian gravitation had worked so well in most of the other cases. The fourth possibility, the one suggested by Bouvard, was that there was another, unseen planet further out from the Sun than Uranus, invisibly pulling on it, thus creating the deviations. While possibilities 2 and 3 argued for hypothesis modification for Newtonian mechanics, Possibility 4 said that it was our picture of the solar system that needed to be modified. Now, due to the slowness of Uranus's motion in its orbit, it took a while for the discrepancies to really show up, and then a bit longer for astronomers to kind of take them seriously. And so it was over a decade before anyone else tried to resolve the problem. In the meantime, Le Verrier took his position at the Polytechnique and found that in the 13 years since Laplace's death, no one had really taken up the man's research program and extended it any further than what he had done. While Laplace had set out the general theory and had applied it in some specific cases, a general solution for all large objects in the solar system had not been done. And so, in 1837, Le Verrier took up the challenge and got to work. Over the next 2 years, he recalculated the theoretical orbits of the inner planets, this time taking into account all of the various gravitational pulls from all of the other known planets. In 1839, he published his results. While not the most original piece of research, it was impressive nonetheless, and it established his reputation as a mathematical astronomer with some real talent. It would also set him on the road for what would be one of the most consuming projects of his life. As we'll return to this in our next episode, I don't want to say too much now. But in his work, Le Verrier found that the inner planet that was hardest to get right was Mercury. While his solutions weren't bad, they didn't give predictions that completely matched those of the planet's actual motion within observational accuracy. As such, he determined that he would endeavor to return to the data being accumulated on the innermost planet's orbit and work out a correct set of equations that took into account the full gravitational interaction between Mercury and Venus. Over the course of the next few years, he did this, coming up with a new, more accurate model that gave better estimates of Mercury's mass and got the predictions to within observational accuracy. The big test of this was to be the solar transit of Mercury on May 8, 1845. Le Verrier's model predicted the precise time the disk of Mercury should begin to travel across the face of the sun. But when astronomers in Cincinnati, Ohio, observed the event, it turned out that actually happened 16 seconds later than Le Verrier had predicted. 16 seconds. A tiny amount. Better by far than any previous prediction, but too big for the precision of the French astrophysicist's calculations. And had not another problem interrupted Le Verrier's research, he would have immediately gone back to the drawing board to try to figure this out. The thing that interrupted him was that Bouvard's Uranus problem was getting to be too much of an issue to ignore by this point. It was becoming something of an embarrassment, and so more and more attention was being turned to the problem. It was Bouvard's nephew, Eugene, that made the first serious attempt to work out that new planet solution to the problem. While he failed in the attempt, his report to the French Académie of Sciences galvanized others to try to do the same. One so galvanized was the British astronomer John Couch Adams, while another was François Arago, the director of the Paris Observatory. Arago disagreed with a number of other astronomers that there wasn't enough data on Uranus to try and mathematically determine the position of a yet undiscovered planet, and thus he decided to get his best man on the project. That man, of course, was Le Verrier at the Polytechnique. Over the course of the next year, the younger man labored away on the problem, eliminating all sorts of other possibilities until the only viable solutions were either that Newton was wrong or that there was another planet. He then set out, figuring out where that other planet would have to be in order to produce the deviations observed in Uranus's path through the heavens. While this was a pretty standard type of celestial mechanics problem, establishing the equations left Le Verrier with 13 things he didn't know, 13 variables. Way too many to come up with a solution in a time without computer simulations to check every possibility. So what he did was, in a word, think. He realized that if he made a few assumptions about the unseen planet, he could simplify the equations quite a bit. So the first thing he did was say that since all of the other planets more or less orbited the sun in the same plane, roughly lined up around the sun's equator, this one probably did too. He also said that it couldn't be too small or it wouldn't have enough influence, and it couldn't be too big or it would have already been seen in a telescope. Now, for my money, I think the next assumption is the real winner here. Remember that the Bode-Tydeus Law is still out there, and it predicted that if there were to be another planet, that planet would be about 39 or 40 astronomical units from the Sun. But Le Verrier realized that if the unknown planet was that far out, it would have to be so big as it would not only influence Uranus, but it would also influence Saturn's motion as well. Thus, he made the assumption that the planet had to be closer and a little bit smaller than what might have been predicted by the Tydeus-Bode Law. To me, that tells me that Le Verrier is willing to put the physical laws of Newton above the seemingly successful but unexplained mathematical relationship of Bode and Tydeus. Once again, this really signals that shift that we see starting with Newton and moving forward towards a truly scientific way of thinking. These assumptions allowed Le Verrier to get his number of unknowns down to 9. A difficult thing to calculate, but not impossible. With a bit more mathematical trickery and cleverness, Le Verrier was able to get to a set of equations that he could grind away on, and in August of 1846, he was able to produce what he felt was the position of the unknown planet. At about this same time, across the channel, John Couch Adams was arriving at a similar conclusion. When Le Verrier announced his findings and asked the observatory at Paris to observe in the region of the sky, about 5 degrees east of the fourth brightest star in the constellation of Capricorn, for an object that would look like a disk about 3.2 arc seconds across, they then went to their telescopes and did nothing. Well, not nothing, actually. They sort of ignored his recommendation and carried on with whatever their research was without giving the possibility of discovering a new planet a second thought. In England, Adams was having about the same set of results to his recommendations made to astronomers at the Royal Observatory and at Cambridge. It's a really weird thing that the director of the Paris Observatory, who had drafted the best mathematical astronomer in all of Europe to solve a problem, when that person did solve the problem, the observatory's director just sort of ignored it. It's just kind of stunning, and one has to wonder if Le Verrier's somewhat imperious personality might have had something to do with it. After a month of pleading and cajoling to no result, Le Verrier started to look elsewhere to see if there was anyone who might take some time to give a look. Over the course of the previous year, an astronomer at the new Prussian Royal Observatory, one Johann Gottfried Galle, had attempted to form a collaboration with the Frenchman, but for a variety of reasons, national competition not the least among them, Le Verrier had not taken the German up on the offer. Now, with nowhere else to turn, he reached out and asked if the staff there in Berlin might find some time to train their telescope to the region of the sky he had calculated the planet would be in. On September 23rd, as the gas lights in Berlin were turned out, Galle, who had obtained the grudging permission of the university's director, stepped up to the eyepiece of the observatory's main telescope and began to call out the coordinates of various objects that he saw through it to an assistant, who checked them against the published positions of stars on a very up-to-date charts possessed by the observatory. At around 1 a.m., Galle called out the position of an object, and for the first time, the assistant, Heinrich Ludwig der Rest, paused and then blurted out, "That star is not on the map." He then ran to awake the observatory director, who came and with the other two observed the disk, exactly the size Le Verrier had predicted, for the next hour and a half until all three were convinced that they had, indeed, found a new world. And while there would be a good bit of nationalistic controversy over both who discovered the world, with the British claiming that Adams should be named as co-discoverer for his independent calculation, and also what to name it, with the immodest Le Verrier suggesting it be named after him for a time, the planet Neptune would soon take its place alongside the other 8 or 9 or even more planets, depending on what one called objects like Ceres and Pallas. With the demotion of those worlds, though, to asteroids in 1850, Neptune would become the 8th planet on the list. As we celebrate the discovery of Neptune, however, let us also take a moment to recognize that Le Verrier's work was considered at the time to be the crowning achievement of Newtonian mechanics. With nothing more than orbital perturbations, Le Verrier had used Newton and nothing but Newton, albeit in Laplace's formulation, to find that which was completely unknown. Instead of refuting Newton's conceptualization of gravity, the inaccuracies in the predictions of the motion of Uranus had enshrined both them and the idea that science was now a fully mathematical philosophy. If there can be said to be a time when natural philosophy comes to an end, this may very well be it. Additionally, the discovery of Neptune spelled the end, at least for a time, to the validity of the Tydeus Bode Law. Neptune ended up being at a distance that contradicted the relationship, and so what was once something that seemed like a beautiful theory was slain by a single, ugly, killer fact. At least for a while. At this point, I think we're at a good place to break our narrative for this week. While Le Verrier's career has another act, and we still have yet to meet Clyde Tombaugh, trying to squeeze in all of that would result in an episode that slights those accomplishments, I think. As such, let's hold off on telling those stories and maybe a couple of others until later in the podcast. As I wrap this up, let me once again remind you that there's a lot more information regarding these topics to be found at our website, thescientificodyssey.typepad.com. We often post additional information there, as well as implements to supplement the audio, and so if you're so inclined, check it out. We also, of course, have the Facebook page for the show, where we occasionally post additional information and articles related to the topics we're discussing. Remember, if you have pictures of any of the things that we've been discussing or talking about, you can post them there at the Facebook page for all to enjoy. I'd love to see something related to Le Verrier if any of our French listeners would like to contribute. Thanks to everyone who gave us some feedback on the first round of graphics. We'll have a second set up fairly soon that's based on that feedback for you to give us some more input on. Also, in something I hope to do with a bit more regularity, let me send a shout out to all of the crew in the Washington, D.C. area. There are a whole bunch of you D.C. lab rats who regularly download the show and give it a listen. It's great to have you all aboard, and maybe someone up there can organize a gathering of the crew through the Facebook page or on Twitter using the hashtag Scientific Odyssey, all one word, and then, post a few pictures of the gathering for the rest of us. For those of you who are scientists up there, we know that you're feeling like you're under a bit of siege just right now. Know that we here at Odyssey headquarters stand with you. Finally, if you haven't been over to the website for the Blue Dot sessions, you should stop by and check it out. They've done a complete redesign of their website to make it easier to explore their music based on mood, or instrument, or energy level. If you're like me and you enjoy having some good music that doesn't intrude too much while you're doing your various work-related tasks, I would really recommend you check out their stuff. It's absolutely fantastic, and I know you'll enjoy it. Now, before we talk about Mercury, Pluto, and the Kuiper Belt, I'd like to do a short detour next week to look at the lives of that most astronomical of families, the Herschels. So until then, full sails on your journey.